Welcome back everyone to yet another video on fluid mechanics. In this video I'm going to talk about pressure measurement equipments. I'm going to show you a couple of instruments that are conventionally used for pressure measurements. So we know there is a, if there is a fluid column or if there is a liquid, a column of liquid, the pressure at its base is usually associated with the height of it. So there is a relation between the height of a liquid column and the pressure at its base. So let's consider a fluid flowing through a pipe, and let's see how we can make an assessment of the pressure as a height unit. So this is a cross section of a pipe, and I'm going to connect an extension on the top surface of this. So if you look through the cross section of a pipe fitted with an extension where a fluid is flowing through, you will see, depending on the pressure inside the pipe, you will see a certain height in the vertical extension, and that height is a representation of how much pressure is exerted within the pipe. So let's say this height is the unit of the measure of the pressure. So how can you relate this to the pressure? So basically the pressure in the pipe is a function of density and the gravitational force, and that is related with the height of this liquid column with this relation. So H equal to pressure inside divided by rho of the liquid, or density of the liquid, times the gravitational force. Or you can also say H is the pressure head of the pressure P exerted within that pipe by that fluid, the flowing liquid or fluid or whatever that is flowing through the pipe. Now using this analogy, let's consider a couple of arrangements of manometers. I don't know if you heard of manometers, but they are the devices with suitable devices suitable for measuring pressure difference or pressure within a pipe or a setup, or the pressure difference between 2 points in a liquid flow or a fluid flow. It depends on the arrangement of the manometer that we create the relation, but fundamentally that is based on the pressure head that we discussed just in the beginning of this video. So again, let's consider a flow of liquid through a pipe, and we are going to connect a manometer in this arrangement. So instead of going vertical straight away, this is a U-tube manometer. So you will see when I complete this drawing that there is a U-bend within the manometer, and that is a method used for conventionally used for measuring pressure inside a chamber or inside a pipe. So let's say a fluid is flowing in the pipe or through the pipe, and we're going to fill the manometer with a liquid that has a higher density than the liquid that is flowing in the pipe. So let's say we are going to fill the manometer with mercury, for example. You can use pretty much any fluid as long as that is denser than the fluid in the pipe. Now you will see, depending on the pressure inside the pipe, the level of the other liquid will vary within the right hand side of the vertical column. So I have shown a couple of lengths here. So one is the height of the vertical column on the right hand side, and next is the to the center of the pipe. So I'm going to call them X and Y, and we have a pressure within the pipe, and we also have atmospheric pressure applied or acted on the top of the right hand side pressure column. So that's atmospheric pressure acting on the right hand side of the manometer, and you have a pressure, say P1, acting within the pipe, and we need to find P1. And when you know the densities of these liquids and also the heights x and y, you can create a relation. In this case, you say this is an arrangement where P1, the pressure inside the pipe, is greater than the atmospheric pressure, and that's why the right hand column is above the datum line on the U. So that is exceeded that line. So the pressure P1 is greater than the atmospheric pressure. Now we can balance the pressure within the manometer using the total pressure on the left hand side is equal to the total pressure on the right hand side of the manometer. So total pressure is P1 is the pressure of the fluid in the pipe, plus you have a density of fluid A and gravitational force times height of that column is y plus x. So that's the total pressure, and that will be equal to the pressure on the right hand side, which is atmospheric pressure plus density and gravitational force and the height x. So that's the pressure balance in this arrangement. Now let's consider another arrangement where pressure inside the pipe is smaller than the atmospheric pressure. The arrangement is pretty much the same. You have a pipe with liquid fluid flowing through it. You know the density of that liquid, and you probably want to find the pressure of that liquid flow or fluid flow. So you create the similar arrangement. You connect it to a U-tube manometer, where you have another liquid of known density filled to get the pressure heads. So what's difference in this arrangement is the pressure in the pipe is less than the atmospheric pressure. So P1 is less than the atmospheric pressure in this case. So you have the liquid flowing through the pipe, and you have a certain height of the liquid. Excuse me. And then the pressure in the pipe will decide how much the second fluid or the manometer fluid will rise or lower. Now, as you will see here, the manometer liquid fluid is occupied a higher position on the left hand side of the U-tube manometer, which means the pressure inside the pipe is less than greater than the less than the atmospheric pressure, greater than the atmospheric pressure in the original arrangement. In this case, the pressure atmospheric pressure is greater than the pressure P1. Again, you balance the left hand side to the right hand side. So the total pressure on the left hand side of the manometer is equal to the total pressure on the right hand side of the manometer. So you have the pressure P1 acting within the pipe, so that is lower than the atmospheric pressure. So let's see if we can balance it. So basically the pressure balance gives you an equation where P1 plus density of gas or liquid in the chamber A, density of the gas A, times G times Y, plus you also have density of gas liquid B times G times X. These three factors or these three components act on the left hand side. So you have rho A G times Y plus rho B G times X. That is the total pressure of these two liquids, and then that will be equal to the atmospheric pressure. There is no other pressure or balance on the right hand side. So with that, I conclude this video. Please comment if you need any other specific topics in the comment box, and I will upload the videos where I can. Thank you again. Thank you very much.